All right, so we're going to look at partial fractions again. And this time we're just going to look at when the denominator is not two linear factors, but when you have a what's called repeated linear factor in the denominator. So you have something like ax plus b, excuse me, all squared. And basically, if you have that situation, got sort of a repeated factor in the denominator, there'll be partial fractions of the form a on ax plus b and b on ax plus b all squared. So that this is all just for that repeated factor. And if there's any other linear factors there, they also get their own partial fraction. So I think, again, the best way to do it is with an example. This example turns out to be a lot harder than I thought it was, but nevertheless, we'll give it a go. And yeah, we'll see how we go. So it says resolve this 3x minus 4 over 2x minus 3 multiplied by x plus 5 all squared into partial fractions. So the first thing we want to realize is that we've got a repeated root in the denominator. So we're going to need both of these plus an extra partial fraction for this linear factor here. So we're going to get something like this. A on 2x minus 3 plus b on x plus 5, which is this part, and c on x plus 5 squared. Okay, and so, yeah, that's what we have at the moment. That's how we need to set up our partial fraction equivalence. Okay, and then the next thing to do is what we're going to do now is we're going to multiply all of this right-hand side by this denominator. So what you'll get is this, and it's going to look very messy, but let me explain. This first fraction, a on 2x minus 3, is multiplied by 2x minus 3 and x plus 5 all squared. So then what you'll notice is 2x minus 3 and the numerator and the denominator will cancel out. Okay, same idea with b here. Multiply 2x minus 3 and x plus 5 squared there. So you'll see that one of the x plus 5s on the top will cancel with the one in the denominator. And the same idea with c. Okay, once you cancel a few things down, you'll get the following. Okay, all the denominators cancel out. And so you're left with 3x minus 4 equals all of this stuff. Okay, and then what you have to do is you need to pick certain values of x. Now, this might be a bit of a tricky idea, but what we're going to do is just going to pick strategically values of x to help us solve this equation, because what we really want to know is what a, b, and c are. Okay, so if we pick values of x and sub it into the equation, we'll be left with some simultaneous equations that we can solve. So the first one we're going to pick is -5, because if x is -5, then -5 plus 5 is 0. So this first term will go to 0. So let's see what happens if we do that. So everywhere we see an x, we're going to sub in -5. So we get all this stuff, including on the left-hand side, we sub in x being -5. Anyway, so we get all this, and then it simplifies nicely to literally this. This left-hand side is -19. This goes to 0, this goes to 0. So you're just left with -13c. And finally, you get therefore c equals 19 on 13. And there's our first answer. This c value here is 19 on 13. Okay, now what we're going to do is we're going to pick another x value. So first we picked x equals -5. Now we're going to pick a different one. I encourage you to think about what we should pick, but a good number to pick would be whatever's going to make this bracket 0. So if we picked +3 on 2 as our next x value, that would be a good idea, because that's going to cancel this one out and this one out. So for x, we're going to sub in 3 on 2. And so we'll be left with this. And then from there, you just make a few simplifications, and then you can solve for a. So, a half equals a times 169 on 4. Divide both sides by 169 on 4 gives us this. So a is 2 on 169. Okay, so now we know a and c. We don't know what b is yet, and this is where this question was a bit harder than I thought. What you need to do now is just pick any other value of x. Pick anything you like, because there's no other value we can pick that's going to cancel these x's to be 0. So we can just pick anything, because really we just need to find b. So I'm just going to pick x equals 0. If you pick x equals 0, and you get a pen and paper out and work it all out, you'll get something like this as an intermediary step. You'll get the left-hand side being -4. That should make sense. This whole thing, when A, we know, remember that A is 2 on 169. So this first part will become 50 on 169. You'll get -15B minus 57 on 13. Anyway, I'll leave that to you to work that out. But basically, you'll get B equals -1 on 169. And finally, this ominous blue box can be filled in. Our partial fraction decomposition for this fraction is 2 on 169 multiplied, no, 2 on 169 multiplied by 2x minus 3. That's this first part. Minus 1 on 169 by x plus 5 plus 19 on 13 by x plus 5 squared. Okay, so just recall that if you turns out that your coefficients, your a, b, and c values are fractions, then you just need to write them as fractions in your final answer like that. Okay, so hopefully that explains a little bit about how to do a partial fraction when you've got repeated linear factors in the denominator. If we go to here for a problem that you can try out, see if you can try this one out. This one will be a bit simpler than the previous one. So resolve 2x plus 3 on x minus 3 squared into partial fractions. Just because I like to see the graph. Here's what the graph looks like. Not that you need it to answer this question. This graph is very interesting though, just looking at it. These asymptotes, this horizontal asymptote is different here than it is over here, as you can see. So interesting looking graph. All right, hopefully that explains repeated linear factors, partial fractions.